Okay? I'm showing what closed loop poles, not open loop poles. What is happening to closed loop poles as we increase the magnitude of Kc. So you see at the beginning, no oscillations. Once you reach that Kc value, you start having oscillations. As long as the dominant, which is the rightmost pole, replaced here by a complex conjugate pair, as long as the dominant becomes more and more negative, you are doing better in terms of offset and things like that. But eventually, they are going to head this way. What's here? All this part is magnitude of Kc less than Ku. You are unstable when magnitude of Kc is greater than Ku. And you are at the verge of instability means you have a complex conjugate pair with real part 0. Not negative, not positive, 0. So at the verge of instability, many years ago, when I was early in my career, I was doing research in process control, and one method that I published was controller tuning with adaptive controller tuning with the Ziegler-Nichols method. Essentially, the method was you use the experimental data as your process is running to identify an approximate model, and then you solve the approximate model for the value of Kc that gives you complex conjugate pair with real part 0. And I will give Ku, and you get, and as a matter of fact, the poles being plus or minus I omega, that omega is the frequency of the ultimate. Ultimate period is 2 pi over omega, omega being this distance. But anyway, why did I put up that? I put it here. Remember, I started all this by saying we could conceivably do it experimentally. However, in reality, no, if you want to keep your job. Why? Let me ask you something. How long have we learned to estimate how long it takes to reach steady state?
Forever?
Four dominant time constant, right? Time to reach steady state is okay. Time delay plus 4 time dominant time constant. What's the tau dominant? Remember, it's -1 over the real part of P dominant. What happens as I approach the ultimate gain to the real part of P dominant?
Infinity.
It goes to infinity. So, to see if you have sustained oscillations or not would take an awfully long time. And how would your system be behaving all this time? I drew it there with oscillations small, but those sustained oscillations could be huge. So you have your sensitive reactor going bang, 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 bang for very, very long periods of time. Okay, so even though theoretically you can think, okay, well, I can do it experimentally, practically speaking, no. With me? Okay? So you understand, to summarize the main concepts here. The Ziegler-Nichols method relies on 2 system characteristics, the ultimate gain and the ultimate period. They are the proportional controller gain that would bring us to the verge of instability, and at the verge of instability, the ultimate response will be periodic with the period, the ultimate period P. Yes, Charles?
So the ultimate period, that's as time approaching infinity.
Yes.
And
yes.
So using the P control, that's as close as you can get to the set point without using integral derivative. Is that as close as you can get without bringing those in?
I guess in a sense, yes. But so, if I'm not going to do it experimentally, well,
So here you say Kc equal Ku.
yeah,
Over there, Kc equal Ku over Q. I don't understand the
that's tuning for good control. Is this a good controller? Kc equals Ku? No, that's terrible behavior.
So
We don't want that tuning. We want our systems to behave nice. We don't have to go crazy. So that's Ku is not a tuning level we would want to use.
Ku is the property of the process, Kc property of the controller.
Yes. In a sense, yes. So, if I'm not going to do it experimentally, how can I find Ku and Pu otherwise? Well, we know we can do small step change experiments. That's okay. I mean, yes, you're not going to lose your job if you increase the flow of the coolant by 5 or 10%. Okay? If you just change the system a little bit and for short periods of time, as long as it would take to reach the new steady state of a step change. There are even methods where you can do a pulse, which is step up and step down, okay, to get the first order plus time delay model. So we can get a transfer function. If I have GU, anybody has any idea how I can find KU? With what we have learned already in this class? So I have a real system.
You take the limit as time goes to infinity to start?
Of what?
I don't know.
I have a real system. I did my step changes. I have my GU. Any idea how I can find KU without doing any other experiment? Just having GU. How can I find KU?
It's in the standard.
Do we use UT and then dictionary it and then take the time?
I'll give you a hint.
Lean on it. You like to? Yeah, there you go.
All right. The hint is on the board. So, Ziegler-Nichols tuning? No, that's what I'm trying to find, the KU. How am I going to find KU? Okay. Okay, Thomas's body plot. Body plot of what? What do I do, Adam?
Where log AR.
Of what? No, tell me body plot of what? What do I do the body plot of? Turns out we are ultimately almost correct, but we have both stability criteria requires body plot of what? Ashley.
G0L, which is the
GOL, okay.
Yeah, I thought it was over.
Yeah, it's not GOL, okay. Open loop.
Right, which is Kc times Gu.
Excellent, Ashley. So, I don't know KU, but I have GC. I can do a body plot of GC, KC, as Ashley said, GOL is going to be GC, KC. I don't know KC, but what will be if I find the right KC at KC equals KU? What do you think will we have? If we are closed loop stable, what do we have?
180.
Amplitude ratio at omega C naught.
Would be 1 the log.
Okay, Adam said it, but let me walk you through it. If I use a KC, if KC less than the minus KC, I'm going to be open loop stable, a closed loop stable, sorry. Closed loop stable, which means that the amplitude ratio at omega C naught, which is the magnitude of GOL, which is GU, oh, oops, GU. Please correct that. What did I put? Ah, really bad. Now, good. Okay, since I messed this up so badly, let me go back. GOL, as Ashley correctly said and I incorrectly wrote, is GUGC, GUGC, and for P control, GC is KC. So everybody okay? That's the GOL. Product of everything in the loop. What is our loop? Our loop is GC, but for P control, GC is simply KC. GU. So GOL for P control GOL is GU times KC. Clear, everyone? If I have just P control, GOL is GU times KC. So I would do, if I try value of KC, and I try the value in which magnitude of KC is less than KU. I don't know what KU is, but if I try something in which magnitude of KC is less than magnitude of KU, I will have closed loop stable, which means the magnitude of GUI omega C naught KC will be less
So
than.
you're saying magnitude, but then you wrote absolute value.
Yeah. KC is absolute value,
Oh,
but
okay,
GU is magnitude. For the scalar is absolute value. For a complex number, KC is real. Right?
Yeah.
If I have tried a KC that is greater, then it would be closed loop unstable, which means that the magnitude of GUI omega C naught times KC would be greater than 1. So, any wild guesses, if I have hit it right on the nose and I have picked KC exactly equal to KU,
That's equal to 1.
then it would be on the verge of instability, and okay, so give me a question.
No,
Handwriting question?
no, I'm good.
Is that okay? Andrea? All right. So that immediately suggests a method I can do. I can try a value of Kc. If amplitude ratio to omega C naught is less than 1, try with a higher value. Higher value. Higher absolute value. Absolute value in high. For complex numbers, it should really be magnitude. For scalars, both would work. And what I can do is try one low, try one high, sandwich between, and then do some interpolation, and just do this different times. Remember, that's all simulation, so it's very, doesn't cost any money, other than your time, right? So I could have an interpolative procedure to try different cases. So for example, I could do something like, and it's best if you do the interpolation with log of AR. So if you try, for example, let's say GU of 0 is negative, in which case, oh, by the way, this is a procedure. All those tuning methods are for open loop stable systems. So for an open loop stable system, if GU is negative, what should be the sign of KC? Negative. Remember, the sign of KC is the same as the sign of GU of 0 for open loop stable system. So KC has to be negative. So let's say I tried KC equals minus 0.01, and I found that log AR equals, for example, 0.2. So I'm below, the magnitude is below the magnitude of KU. With me? If I try a value and I find that log AR and AR being the product of GU times KC, the magnitude of GU times KC, okay? Then let's say I try something much larger. Let's say I try KC equals minus 1. And let's say I find log AR at omega C naught. At omega C naught. I wish I had time to be doing this iterative procedure on the computer, but since I'm short of time, I have to find ways to be more efficient.
Do we have to use Excel for this?
Let's say 1.4.
Do we use Excel?
But that's 18 then.
Say again?
The second line.
It says then.
This?
Oh, that.
Then.
Oh.
Yes.
Are we using
So, what would be a next value to try?
Oh.
Linear interpolation, right? What am I trying? Oh, oops.
What is that?
I have put log. I messed up. Okay.
try then?
Stable, log should be negative, so let's say minus 0.2.
Huh? Try.
Let's say I'm stable. Let's say I found plus 0.4. Because I put log. AR less than 1, log AR negative. Okay, please correct that. Bree, am I confusing you? Are you okay? Robert? Robert? Robert?
Is this a computer part?
What do you mean?
Because are we gonna have to sit there and guess in the exam, or we just type it in Excel? We don't find it.
Just stay with me.
Okay.
Just stay with me. Just understand the concept, guys. Don't worry about the exam. If you understand the concept, you're going to do great. If you don't understand the concept, you just try to mimic things, you may not do well. So try to understand the concept. So, what I'm trying to say here is, you can do a trial and error method guided by interpolation. So you try first a small magnitude, and let's say you found log AR at omega C naught is minus 0.2. We are stable, therefore this magnitude is less than the ultimate gain. We try something much higher. And in this case, we found positive. So we're on the other side. What's the next trial we try? What am I trying to get?
0 or 1?
I'm trying to get to 0, the log to 0.
Oh.
AR at 1, log at 0. Okay, so maybe my next try would be if you build a linear model, you know all linear interpolation, right? Ready to go over it? Okay. So then you interpolate and keep interpolating until close enough to 0. So that would be a procedure we can use. However, luckily, we won't have to do that. Okay?